Okay, in this session we're going to talk about some applications of set theory. Um, uh, First, there'll be a few problems I'll work through dealing with set theory. Then I'm going to talk a little bit about set theory and internet searches. There's a lot of the background work behind the search engines that Google designs and other things is this concept of set theory, how to sort and organize data into different groups based on what someone is looking for. But first, a few problems dealing with set theory. Where I'm going to start is with the investigate the math discussion on page 179 of your text. And it sets up a description and asks for a certain point of data. And we're going to work through that. So, in this investigation, Rachel surveyed grade 12 students about how they communicated with friends over the previous week. 66% called on a cell phone, 76% texted, 34% used a social networking site, 56% called on a cell phone and texted, 18% called on a cell phone and used a social networking site, 19% texted and used a social networking site, and 12% used all three forms of communication. Ultimately, we're asked to find what percentage of the students involved used at least one of those types of communications. So, let's talk a little bit about the different sets that are involved. U, our universal set, is all grade 12 students surveyed. I'll call C all students who called on a cell phone. And yes, the book is a little bit dated, so people are calling and texting and using social networking sites instead of, I don't know, whatever you guys do these days, tweet, TikTok, what have you. T is all students who texted, and S would be all students who used social networking. Now, first I'm going to describe the numbers that were given to us in terms of the symbols that we've been using. First out, we don't know how many students there are in total, but everything is listed in terms of percentages. So I'm going to talk about my numbers in terms of percentages. My universal set is 100% of the information. All of the grade 12 students surveyed. My first statement is 66% of them called on a cell phone, so the number in the cell phone group should be 66. 34% used a social networking site, or I jumped over texting, 76% texted, so the number that texted is 76. 34% used a social networking site. So far, so good. But now a couple of other statements where we need to dig into these concepts of intersecting sets and unions of sets. 56% called on a cell phone and texted, meaning they did both of those things. So in our notation, called on a cell phone and texted would look like the intersection of those two sets, everybody who did both of those things. And we know that 56% did that. By the way, this number should always be equal to or less than the numbers in the two sets that made it up. That is the intersection of the sets. If it was the union of the sets, it should be bigger than or equal to. Next, we are told 18% called on a cell phone and used a social networking site. So called on a cell phone and used social networking. That was 18%. 19% texted and used a social networking site. And 12% used all three forms of communication, and what that looks like is the union of those three groups that we talked about, and we know that that is 12. There's two ways you can approach a problem like this. One is to draw out a Venn diagram and just sort of work through the diagram. Another is to use the diagram to set up some equations that you can use. So start by drawing out a Venn diagram of the situation. This is my universal set, in which I've got three other sets that all overlap each other. Ooh, that's a terrible circle. Which I will call cell phone group, texting group, and students who use social networking. And ultimately what we're interested in is what percentage of students used at least one of these, and that would be the number that's in the union of all those sets that we're interested in. So first I'm going to set up the math, but then I'll show you how you could just use the diagram itself to work this out. So if I want what's in the union of these three sets, that basically means I want everything within the shaded area. But I can't just add up what's in the three groups, because that's going to give me a bunch of overlaps. If I just add up the numbers in these three sets, then I'm going to have this area of overlap, this area of overlap, and this area of overlap. Those have all been double counted. So that means that from this total, I would have to subtract the number that's in the intersection of C and S, the number that's in the intersection of C and T, and the number that's in the intersection of T and S. Now, the last problem comes in this middle region. I counted it 3 times when I added up C, T, and S, but I got rid of it 3 times when I took out those 3 areas. So I've actually triple subtracted that center area after I triple added it. So that means it's completely gone from my numbers now, so I have to add it into the end, and that is the intersection of all 3 sets. So this should give me how much is in that entire region. The numbers in C, T, and S added up, minus the overlaps, plus the middle overlap that I would have gotten rid of completely when subtracting. And so now if I just do that by the numbers, the number in C was 66, the number in T was 76, the number in S was 34, the number in the intersection of C and S was 18, the number in the intersection of C and T was 56, and the number in the intersection of T and S was 19, and lastly the intersection of all 3 sets was 12. If I work that all out, 66 plus 76 is 142, 142 plus 34 is 176, 176 minus 56 is 120, 120 minus 18 is 102, 102 minus 19 is 83, 83 plus 12 is 95. Which seems to imply to me that there are 95% of students who used at least one of these methods to communicate with people in the last week. And now a little bit about how we could work this out from the numbers we're given in the Venn diagram. We know the intersection of all 3 sets has to have 12% in it. The intersection between T and S has to add up to 19, but 12 of those are already here, so that leaves 7 more there. The intersection between C and S has to have 18 in it. We've already got 12 in the center, so that's another 6 out here. The intersection between C and T has to have 56 in it. There's already 12 in the center, so that leaves 44 out there. I apologize for that one being a little on the tiny side. And now I know that there's got to be 34 people in total in set S. You're already accounting for 7 plus 12 is 19, 6, 25 of them here. 34 minus 25 is 9. Likewise, group C has to have 66 people in it. You've already accounted for 52 here, so that leaves 14 in that. And lastly, in the texting group, there's 76%. We've got 63 already. That leaves another 13 out here. And if I just add up all these numbers, I'll know how much had to be in the center. 14 plus 44 is 58, plus the 12 is 70, plus the 13 is 83. Oops, hold on. I think I did something a little off here. 19 minus 28, 6, 34. That adds up. 44 and 6 is 50, and 12 is 62. Oh, this should have only been 4, not 14. Because in C I had to have 66 people. I've already got 62 here. That only leaves 4 who just used their cell phone to call. Let me start adding again. 4 plus 44 is 48, plus the 12 is 60, plus the 13 is 73, plus the 7 is 80, plus the 9 is 89, plus the 6 is 95. Which leaves, by the way, 5 left over who don't do either. So 2 ways you can go with this. Once you've identified everything you've been told and set up a Venn diagram, you can put together an equation for the math of it, work that out, or you can fill in the Venn diagram and get your numbers from there. Either way, 95% of the students surveyed used at least one of these methods of communication in the last week. Alright, I'm going to go into another example, similar sort of setup. This is example 1 on page 180, and we are discussing children who own pets. We're starting out with 28 children have a dog, a cat, or a bird. And that is the entire group of people that we're talking about, group of children that we're talking about. So I'm going to make my sets D, as in the number of children with a dog, C, number of children with a cat, and B, the number of children with a bird. I don't know why I stuck a in each of these. Information that we're given. 28 children have a dog, a cat, or a bird, meaning they have at least one of those 3 animals. So that describes the union of those 3 sets. In the union of those 3 sets, there should be 28 children. 28 elements in the sets combined. We're told 13 children have a dog, 13 children have a cat, and 13 children have a bird. 4 children have only a dog and a cat. And I want to stress, first the dog and the cat part will make it sound like the intersection of these 2 sets. But to say they only have a dog and a cat means they cannot have a bird. So there are 4 children who have a dog and a cat, but not a bird. 3 children have only a dog and a bird. So the intersection of dog and bird without cat is 3. 2 children have only a cat and a bird. So the intersection of cat and bird without dog is 2. And the last statement given is no child has 2 of each type of pet. And that's just to say everybody only has 1 dog or 1 cat or 1 bird. Nobody has 2 cats, 2 dogs, 2 birds in this example. And we're asked how many children have a cat, a dog, and a bird. meaning what's the intersection of all three sets? And how many children have only one pet? And so that's going to be the number in D without B and C. I want to make sure I get this intersection notation right. It's going to make it without B and without C. Plus the number in B without C and D. And, yeah, there was a better way to write that. The number in D without what's in the union of B and C. That's the number in B without what's in the union of C and D. And the number that's in C without the union of B and D. So this is what we're asked for in A, this is what we're asked for in B. Now I would argue in this case the Venn diagram with the numbers filled in is probably our easiest way to go. Here's my Venn diagram. Here's my overlapping sets with sets D, C, and B. Alright, so when I get to specific things that I'm interested in, I know that the number of things that are in set D and C but not with B is 4. D and B but not with C is 3. And C and B but not with D is 2. Now the problem that I have with going much further is I don't know what this center part is. So I'm just going to call that center part X. Now I know that C has 13 in it in total, but 6 plus X of it is taken up in here. So what's going to be in C is 13 minus 6 plus X, or 7 minus X. Similarly, D has 13 in it in total, so D would end up being 6 minus X when I work that out. And B has 13 in it in total, so B would end up being 8 minus X. Now if I put all these together, it should add up to 28. So I should end up with 6 minus X plus 4 plus 7 minus X plus 3 plus X plus 2 plus 8 minus X. That should equal 28. 6 plus 4 is 10, plus 7 is 17, plus 3 is 20, plus 2 is 22, plus 8 is 30. Minus X plus X minus X will all become minus 2X. And that equals 28. Or negative 2X equals negative 2, or X equals 1. If I then redraw my Venn diagram with what I just found filled in, put 1 in the center, 4, 3, 2, 7 minus 1 is 6, 6 minus 1 is 5, and 8 minus 1 is 7. Brain fart there for a moment. I can double check to make sure this works out. 5 plus 4 plus 6 is 15. 15 plus 6 here is 21, plus 7 is 28, which it should be. And now that I know what that center is, I can work out what these two values are. The intersection of D, C, and B is 1. Now the number of kids who only have one pet, this is it written out in set notation, but really what it is 5 plus 6 plus 7. So D without B and C is this part. B without C and D, or C or D, sorry. B without C or D is 7, and C without B or D is 6. Put it all together and you get 18. So in answer to our two questions, only one child has a dog, a cat, and a bird. And B, 18 children have only one pet. Ooh, let's right through it. I'm going to do one more example. And you can read along in the book with it, example 3 on page 185. Although in the book it is more set up as a find the error sort of problem. I'm just going to use it as one more example of a problem to work through. And in this example, we're dealing with Shannon's High School starts a campaign to encourage students to use green transportation for traveling to and from school. At the end of the first semester, Shannon's class surveys the 750 students in the school to see if the campaign is working, and they obtain these results. So, our universal set is all the students in the school. And they are surveyed about whether they're using public transit, cycling, or walking to school, as far as green transportation goes. So I'm going to use P to be number of students using public transportation. I'm going to let C be the number of students bicycling. And W be the number of students walking. We're told right off that the universal set has 750 students. 370 students use public transport. 100 students cycle and use public transit. Now you'll notice they don't say only cycle and use public transit. So this is just the intersection of the two sets. "80 students walk and use public transit. 35 students walk and cycle. 20 students walk, cycle, and use public transit. That's the intersection of walking, cycling, and public transit, so that'll be my number in the middle. 445 students cycle or use public transit. And there they say cycle or use public transit, so we got to be careful on the wording. Cycle or use public transit is the union of the two sets, because that could be anybody who uses one, the other, or both. And 265 students walk or cycle, so that again is a union of sets. And then we can try to put our Venn diagram together. Making this one nice and big so we get lots of room to write stuff down. And my universal set, and the public transportation people, the bicycling people, and the walking people. So if I start to fill in what I know that there's 20 people, 20 students, who use all three forms of transportation. Now there's 35 people in the intersection between W and C, 20 of whom are accounted for here. There's 80 people in the intersection between walking and public transit, 20 of whom have been accounted for in there already. And there's 100 people in the intersection between cycling and public transit, 20 of whom are accounted for here, leaving another 80 out there. the total number of people using public transit is 370. 370 minus these three numbers would be 370 minus 100 is 270, minus 60 is 210 here. And that takes us down to our information at the bottom. The number in the union of sets P and C, which is all of this, is 445. So I got to figure out what 445 minus all these numbers are to get that number. 445 minus 15 is 430. 430 minus 100 here is 330. 330 minus the 210 here is 120. 120 minus the 60 here is 60 here. And I'm going to double check that. 210 plus 100 is 310. 310 plus that 120 is 430 plus the 15 is 445. And then similarly, between walking and cycling combined, the union of those two sets, there should be 265 people. So 265 minus the 15 is 250. Minus this 100 is 150. Minus this 120 is 30. So my Venn diagram is mostly filled in. I still don't know how many people don't use any of these things. So if I add up to figure out the union of all these sets, I have 210 plus 100 is 310. Actually, I can do this much easier. I know that the union of C and P is 445, plus this 30 is 475. And that means the number who are not in the union of those sets is going to be 750 minus 475, or 275 people out here. So that's my completed Venn diagram, and ultimately we are asked how many students use green transportation. That's going to be this number, and we can say that 475 students use some form of green transportation. Okay. I think I'm going to leave that there for now. That's the one that I wanted to do. Yes, I'm going to leave that there for now. As far as going through some examples go. One last thing that I want to talk about with set theory that's going to crop up in the set of questions that I give you, and it's also shown in example 2, which will be easier for you to read and follow through than for me to just step through it here. So I'm going to put this here, as well as on the Google Classroom, read example 2 from pages 182 to 184. What that example describes is basically someone trying to narrow down an internet search, which I'm sure all of you have had some excuse to do at some point in time or another. We've all had the experience of putting in something into Google and it being a little too vague, and you're getting back millions and millions of hits because, you wanted to find out when the next episode of whatever was coming out, and instead of searching out the specific episode you wanted, you just typed in the name of the show and got way too many hits. So when internet search engines are sort of trying to parse up the internet and decide what results to return when somebody puts in a query, they have to base it on the words that they're given, but also on how they're given to them. Because there are some tags you can put in when you're searching for things on the internet. Putting an expression in quotes, for instance, means it looks for the whole expression, not just each word individually, which can make things different from a set theory. For instance, and this comes up in the example, if I wanted information on popular culture, which would still return a lot of hits, but if I just type in the words popular and culture, I would get every site that had either the word popular or the word culture in it. Basically, I'd get the union of those two sets, which would be a lot. But if I put quotations around it, then it has to look for both popular and culture, and I get the intersection of those two sets, which makes it much smaller. Anyway, I'm not going to talk much more about that. Read through example 2, and it will talk a little bit more about some of the ways that you can search the internet more efficiently, and also get into a little bit about how these search engines parse up the internet in order to be searched through. All right, that's all I have for this one. Thanks for listening, everybody.